Welcome back everyone, it's Harrier time again. Our 90mm Harrier did his first STOL starts from grass and also super slow STOL landings. And it flies phenomenal. This time all the perfect settings were found and also lots of investigation for our bigger Harrier with the 105mm ADF were done and the results were amazing. So much I can tell you at the first moment. I would say let's start with the video and go into our thrust testing with the Harrier ducting. Let's Harrier ductings that will be tested. The original one for 90mm and two upsized one with 118 and 122% size for a 105mm JP EDF fan. The rear nozzles are removed. First I figured out the difference between front and rear nozzles. 2.1 kilograms we get. Not the same for the front nozzles. And as a result we can see that the rear nozzles got about 60% of the front nozzle thrust. Next is the horizontal thrust. Everything is ready. Let's go. That's almost the same like vertical thrust. This difference is, I think, caused by the battery. This battery is quite new. Now we got here the JP fan, 90mm. The nozzles are fixed to vertical thrust and parallel. Let's start. And horizontal thrust with the 90mm JP fan. So we got a max of 2.7 with super full battery. For evaluating the efficiency of the ductings, I was also testing the EDF alone. JP 90mm. .9 kilogram for the 90mm EDF, and next was the 105mm JP fan. The 105mm fan provides about 400 to 500 grams more thrust in the 118 size Harrier ducting. And here we can see the 122% size ducting. These yellow parts are the gears which will be attached on the nozzles. Everything is printed with lightweight PLA to keep the weight as low as possible. Now the ducting with 122% size, so again a bit bigger. And the vertical thrust with the 122% ducting and the 105mm EDF. Woohoo! This was the best thrust we ever had, over 3 kilograms. That's the best ducting of all. With the small one 2.5 and with the big one 2.9 to 3, and now with the 122%, so again a bit bigger, up to 3.3. This is superb. This is very, very good. This will be our next Harrier. And the battery is still very cool, so with more temperature on the battery I think we'll get even better results, but they are still very good. And the ESC also super cool. Let's see the motor. Everything nice. This is a wonderful setup. Next thing to test is if it would be possible to put the front pitch EDF into the fuselage. This is the area under the canopy. So I think here has to be made some cutouts, but at first we want to see if it works anyway, that it looks more scale. The first step is making a thrust test with the EDF. This is this one, 50mm EDF for 4S, and this should provide at 550 watts about 950 grams thrust. It's a QX motor EDF. Battery is full. And we got 810. This is not correct. We got 140 gram less. Let's see what we got on the installed EDF. Maximum open. Just a little loss, just about 70 to 80 grams. I think this is because of this edge. Air can't get in the same optimum like we saw it on the previous test stand. Here the air can come from all sides, and I think this and this wall reduce the thrust, but nevertheless that's not bad. Let's put on the canopy and see what happened. Okay, I don't know why, but it's getting worse. We lost about nearly 300 grams. I think I will start making cutout here. So that's the first attempt. Here I marked the cutout for the side, and also I will make 3 cutouts in the front window. This one is already made. This will be just a small hedge upper here, and on this side the same cutout with the small knife. Let's see. I made sure that I don't go underneath the upper side from the inlet ring. Fits right with the inlet ring, this bleed hole, and that's the canopy. I think later on we will add these ribs also here, then this looks a bit better. Let's go on testing. Okay, it's better. 40 grams less. I will remove the canopy and do it again. It's still a loss of 100 grams. They have to be bigger, or maybe one in the top. So some cutouts are added in the middle. And about 25 grams more. So this time in the original nose from 90mm EDF with the 50mm front fin. So we got a loss of about 250 grams with just the EDF without this lip. And then we got not the same aerodynamics all around. Here is this big step and here is this sharp edge. Right before the EDF should be a very homogeneous area in one level. So the best is always this inlet lip. Yeah, let's see how we can integrate this on this nose. As result from these tests, we let the EDF in rotate left and to right. I numbered then 1, 2, 3, 4, that everything got on correct position. Leveling the nozzles 90 degrees to the ground, and I will mark the center line. And also on the fuselage I marked 0 position on this teeth and write 0. When this is done, I bring the servos to 100% in the direction they turn the nozzles exactly to this endpoint. I can put on the gears. So both gears are on. It's turned for the first time. This works nice. This is enough for STOL. When we do VTOL, I can go here to 150%, but this is for later. Just in case I would disassemble something, I also mark the 0 position for the gear on this teeth and also on the fuselage with the 0 and give it a number for the 1, that this belongs to this nozzle on this side, and they're the same. And so if something gets disassembled, I know. Here we got a small gap between the two gears, and maybe we can optimize this. I printed the same gear with 60% flow to make the sieves a bit thicker. So new gear is in and perfect. Just a very little gap, but it's okay. This okay. This looks good. Yes, super nice. And 2 nozzles are running. And all 4 nozzles are assembled. Next I want to measure the current when there is no movement. So here we got around 100 milliamps. And when they move, it's about 230. To see that all run with the same friction. Now servo will overheat because maybe here's too much friction or there is something not correct. And the last one, 118, 400. The most, 380. Here seems to be more friction. Pressing the ball slightly to the inside, very slightly. So let's see again. And we reduce this just a bit, maximum 300. 300 is okay. That's nice. And now all nozzles together, 270, 1 ampere. So we got an average of 250 and this is okay. All are equal. Here I am bringing the nozzles to 45 angle downwards and mark this. There's a bit different between the front and the rear, but almost okay. From the front this is good visible. From the front cam in the air. I was adding 1.5 millimeter carbon rods to make this more accurate, visible. And so here we can see the 45 and the 60. This turns out nice. And also important for the pre-flight check that all servos work same. So let's see where all the components can be put on. On this side I will put the capacity sensor. Here we got the BEC, the receiver, telemetry and the gyro. That's an optical ESC, so we don't have a BSC inside, so I make some cutouts here on the power cables and add a small plug for the BSC. Underneath the ESC I put these 4 cable tie holders, so the ESC is a bit lifted up and doesn't touch the lightweight PLA, so it don't get melted, and it is cooled from the upper and the lower side. So ESC is in position, hedge fits, and through the NACA inlet the ESC can be cooled. So I'm wiring using this metal rod, bringing the cables underneath. So step by step to make sure that these screws are secured. I put a red dot on it on everyone and then they should stay in position. So the Harrier is nearly complete, covered with the resin to make the surface a bit more stable and solid. Also the wing, because you want to fly high speeds and maybe these darker colors can be too hot, so it's also more heat resistant. And you can see here all these cables, it's a bad mess all the time. At first I put them here with the small clamps on my wall, but I'm not so happy with this, so I decided to build up this board, this wood board. It's made of 4mm plywood. Oh, let's go.
Come on.
So the Harrier is ready. Let's take a look on the electronics. Here we got the pitot tube for the speed measuring, and also there is the sensor. Here we got one satellite receiver. Underneath is the servo for the wand wheel steering. Of course, there is the JP 90mm EDF fan installed. Here we got our BEC for the 6 volt for all the servos. On the other side, we got a capacity sensor for the main battery to see when it's getting empty. And here, these are the servos for the nozzles. This is our gyro to level up the Harrier, especially when we will fly very slow. This is the telemetry transmitter and this is the receiver. We got not that much cable from the front and they are running here on this side. This side is just for the big power cable. Also the wires from the servos I put underneath. So most cables are underneath, that they are not that visible and not that messed up. Here we can see some pics from the Forerunner, from the earlier version. There were the power cables up here and this was a bit more messy, but this time looking nice and clean. Here we got the elevator servo and down there is the other satellite. Take a look underneath. Our front gear, the ESC for the motors, the rear gear, and that's all. That's the wing. Here we got the outer landing gear, AL servo, flap servo, and the connectors. I wrote some letter on them. For instance, here F for flaps, G for gear, and so on. Power is on. Let's do a checkup. Start with the gear. Yeah, it's coming out on the wings also. Then next is the rudder. Okay, it's working. Once we're together. Throttle. Yeah. Engine is running. Okay. Elevator. Yeah, it's running. AL. Here I got one switch and this moves the nozzles, sets the gyro and also moves the flaps. Now we have flight mode 1, now we have 2 and the nozzles go to 45 degrees and the gyro gives much more input. The gyro gain is much higher because this is for STOL, for flying slow, and as slower we fly, as more stabilization we need. And also the flaps go a bit down, and when I go one step more down with the switch, you see the nozzles go to 60 degrees. We are in flight mode 3 and also the flaps move a bit down. And now the gyro is much more doing quite a lot because this is for super slow flying and this will be very interesting if the gyro can keep the Harrier in level. So let's check up the telemetry. Here I have this air gun. Okay, that's working. Next is the capacity sensor. It's also working, so the technique is working. Then I would say, let's assemble. Harrier is ready assembled. Let's take a look to one of the most interesting points, to the weight. 2135 without battery. And batteries will be used two types. There's 4000 milliamps with 615 grams and 5200 with 690. So we got a takeoff weight and 2827 or 26. Yeah, this is quite a lot. This is caused by the gears, I think, and the camera or the balancing weight will be added also. So I think we land short above 3 kilograms. Time for the first thrust test with the Harrier. Everything ready? On 0. Got exactly 2 kilograms of thrust, 130 amps max. For the next test, the nozzles go 45 down and full throttle again. And we got 1200 and next 60 degree and power. 350 grams forward thrust. I will go a bit back. Maybe this Could slow the jet too much down. Battery temperature 40 degrees, okay. For the next test I will swivel the nozzles under full throttle. 0. Okay, this works nice and the battery is just half empty. That's good. This works. Oh, checking the ESC. Warm. The camera is installed and 30 grams of ballast. And now it is leveled on the CG. There we can see it's slightly nose heavy, almost leveled. Just see if there's a difference between the batteries. And again with the smaller battery, but it's the same. The battery is so close to the CG that there is no difference. Okay, it was quite windy on the test flight day. The wind was straight along the runway, so it shouldn't be a big problem. Here are some outtakes from test flying the Harrier last year. And the biggest difference is that we got a retractable landing gear these days. And are not forced to use the catapult. Hopefully the landings will be better than this one, but I'm really looking forward and I'm not that much missing the catapult shoots. Das ist on, Fahrwerk ist in. Die haben mir immer so schnell die Spannung. Reaction test for rudder. Okay, goes on the opposite. Elevator. When the nose goes down, elevator goes up. It's okay. And when the goes up, this goes down. Okay, and AL. Yeah. The wing that goes up, also the aileron goes up. This is okay. Elevator up. Elevator down. AL right. AL left. Rudder left. Right. The mix is also okay. Umschalten, aber mal Start. These first start attempt with nozzles over 45 degrees down went completely wrong because the Harrier doesn't accelerate. So I did a second attempt with nozzles straight horizontal. This was of course no STL start, but the Harrier was into the air for its first time anyway. The jet was a bit tail heavy and also the gyro setup and all the rudder and elevator and also on settings were not that good, so I decided to make the first landing on the skids after flying some patterns. So I'm adding 10 grams of ballast. So now I was reducing the way of travel just under 45 in the first step and 245 in the second, that we got more thrust forward. The second start attempt with nozzles about 25 degrees down went much better. But the Harrier was still tail heavy, so I came back for the second belly landing. Nevertheless, all these first changes in the flight settings make the Harrier fly much more comfortable. And this third takeoff looks really STL-like. Okay, Mittelstellung. The Harrier lifts off at most exactly 60 km/h, and this is for this little airplane with the heavy wing load really slow. The normal flight speed was between 70 and 80 km/h, but it was also possible to go down to 60 with nozzles to 25 degrees or a bit more down. These blue strands make the airflow visible, and this is super clean, so we got all the time lift. Even while turning, I felt never any spin or stall tendency. The Harrier was just flying wonderful on this super windy spring day. While this flyby, we saw that the airspeed goes down till 54 km/h. I think it is also possible to go into the 40s, but this I will try out when it is a bit less windy. And here we saw it 48 km/h, and I'm sure the Harrier can go much slower. So gears down and take a look at the landing speed. It's about also 60 km/h, so the same as we had on liftoff. But here I was flying with a lot of safety. On more calm weather conditions, I think 50 km/h landing speed is also possible. Flying low and slow was a big fun with the Harrier. And here we can see the very first landing on gears on my sweet little airport. The Harrier needs just some meters for start run, and then it lifts off. Flying a jet with sweepable nozzles is a complete new experience. It was absolutely wonderful, and there will be so many things possible in future. This was just the very first experimental flight day, and I'm looking so much forward to bring this Harrier in the air again. This was so much fun with this Harrier. The final settings on the flaps and nozzles and the ailerons and elevator and so on, I will share with you when I've flown the jet on less windy conditions, because this was so windy and so rough I couldn't do a fine setup. But this will follow in the next Harrier video. I'm so happy that we got this 3.3 kilogram thrust out of a 6S LiPo setup, and this bigger Harrier, this 122% size, will be the one which will do the first VTOL start and the first transition. And when we got all the data from this, we will transfer it to the 90mm one, that this will also become a VTOL jet. So I hope you enjoyed the video. Visit our sponsor and take a look down in the comments. There you got all informations, where you got the STLs, how you can support this channel, and so many informations more. Check out my channel if you want to learn more about 3D printing, how this jet is working, how these vortex and all the details. Check it out and have a great week. We see us in the next video. Bye bye.